Welcome to the Futurati podcast. Any member of the Futurati is somebody who believes in the power of the future. We know there's a better world ahead, and we indeed have the power to make it so. In our podcast, we talk to the best minds in the world about the most urgent problems facing mankind today, and we hope you learn as much from them as we do. I'm Thomas Fry, a professional futurist and keynote speaker.
And I'm Trent Fowler, a machine learning engineer and author. Thank you for joining us. Good evening, everyone, and thank you for listening to the Futurati podcast. Tonight, we're joined by Aleksandra Ćiprijanović. Aleksandra is a postdoctoral research associate at Fermi National Accelerator Laboratory, where she works for the Scientific Computing Division on the High Velocity Artificial Intelligence Project. More broadly, she's interested in applying machine learning and data science to astronomy, cosmology, and high-energy physics. If you enjoy this interview, please don't forget to like the episode and subscribe on YouTube or wherever you get your podcasts, and don't forget to check out our new website, futuratipodcast.com. Aleksandra, thanks so much for coming on the show.
Thank you so much for inviting me. This is for sure a very big pleasure. Thank you.
I'm glad to hear that. Why don't we start by hearing a little bit about your background, your interests, and what brought you to doing the research that you do?
Oh, well, I lived until very recently in Serbia, and this is where I got interested in astrophysics, and as I guess every small kid, I was interested mostly in dinosaurs and space. So those two things. And the more people I talk to, the more I hear the same words. But I guess people who end up studying science just never get over that. Right. So I was interested in those two things and ended up studying astrophysics in Belgrade, that is capital of Serbia. So Serbia is a small country in Europe, close to Italy and Greece. And I did my undergraduate and graduate studies over there. I worked also a couple of years at the Department of Astronomy, where I studied as a researcher, and also at the Academy of Sciences and Arts. We have a mathematical institute over there. So astronomy in Serbia is studied, I guess, next to computer science and mathematics mostly, because it kind of grew out of those two sciences. So that's, I guess, my background. My PhD wasn't really that much about what things that I do right now. It was more theoretical, high energy astrophysics. I wanted to understand how, I guess, particles were created after the Big Bang and after that. Eventually I got interested more and more in computer science, in machine learning, and I transitioned more into doing something in between astrophysics and computing. My interests now are kind of in both fields, and I do things that are related to machine learning and how to help astronomers and astrophysicists work on those big data sets that we have from telescopes using machine learning.
Oh, that's fascinating. So I was wondering if we could maybe start with a couple of broad overview questions. So could you talk a little bit about just the concepts involved in astrophysics? Like what's sort of the basic ideas that a person should know from astrophysics to at least be conversant in a discussion between some professionals?
Wow. Well, that is not a very easy question to answer. There are a lot of things. But I think that once people start thinking about astrophysics, we should, I guess, be aware that everything that we see, everything that we know about all of the matter and energy, understanding how that came to be, where we come from, why there is everything around us and not nothing, really came from, from space and from at least what we know now from Big Bang and everything that happened after that. So the creation of galaxies, of stars, and big structures called large-scale structures in the universe. Everything really is governed by, gravity and other forces in physics. And astrophysicists really study all of that. We study the same things that physicists here on Earth study, just applied to space, applied to larger lengths, huge masses, and very high energies, some things that we cannot achieve here on Earth. So, when you think about astrophysicists, you basically, you talk to a physicist, you're talking to physicists, but just a person who, I guess, looks more into the past and how we came to be here and what's going on large scales.
So it's like archaeology for stars, basically. So you did kind of end up in dinosaurs in space.
Exactly.
How would an astrophysicist be different from an astronomer?
So I guess astronomers are, people who first were interested in stars. So they couldn't understand the physical processes, maybe, that, produce all of that they see first without telescopes. And after that, once we built telescopes with telescopes, they measured the behavior of these objects, how they move around. Do they see some regularities or some weird things? And then later on, as people, I guess, learned more physics and understood physical processes, and also very importantly understood that the same principles also govern the cosmos and not only things here on Earth, then they could apply the physical knowledge to the processes they see in space and really try to understand the physics of all of the things that we see around ourselves.
So it's just like an astronomer who's better at math?
Well, both astronomers and astrophysicists have to be really good at math.
Yeah.
Yeah.
So what about a cosmologist? Like, how would you distinguish yourself from a cosmologist?
So astrophysicists, they study particular objects, so stars, galaxies, groups of galaxies, and they try to understand different processes happening in all of these objects that we have around us. But cosmologists, they try to understand the universe as a whole. So how, where did it start from? How did it evolve? How did we get to where we are today? Is it expanding or not expanding? What forces govern this expansion? What, type of matter is inside, and how does that influence the whole evolution of the space around us? So they're trying to really understand the big picture and answer big questions like, why are we here?
I see. Okay. Yeah. It sort of shades over into philosophy if you go back far enough.
A little bit, yeah.
So in doing research for this interview, I was reading your thesis. Contributions of galaxies and galaxy clusters to the diffuse gamma ray background, which was, delightful reading. And first of all, a bunch of it's written in Serbian. So I had to start by learning Serbian. But then once I had that down, this line jumped out at me. And you wrote that for the first time, we include the change of gamma ray production with time through the history of the universe that reflects the evolution of accretion shocks, which appear during large scale structure formation. And I occasionally find myself flabbergasted that we know as much as we know about the universe and the large scale structure of matter and its distribution. And I was wondering if you could just give sort of a layman's overview of the evidentiary basis for that. Like, how the hell is it that we know so much about all these things that are so far away and so massive? I'm just guessing that there's a lot of inference involved, right?
Exactly. I mean, I am also flabbergasted by the things that we know, definitely. And, the more you study, the more, flabbergasted you are, I guess. So primarily, we know all of these things because we are building better and better telescopes. Nothing would happen, of course, without theorists imagining all of these things. But finally, when it comes to space, many of the theories just seem very crazy, and people don't like to believe in them until we get really good proofs or multiple proofs. And one of the things, I guess, that is helping us understand how these large-scale structures form is basically the fact that we have very good telescopes in different wavelengths today. Something called, big astronomical surveys, for example. And these surveys really, they observe the whole sky, and they can see very, very faint objects. And, the fainter the objects that we can see, the more distant objects and older objects we can see. And once we had good enough telescopes, for example, we could see that all of the objects are really not very uniformly distributed. I mean, they are uniformly distributed, but they are kind of producing these clumps, and they are kind of distributed in this different types of filaments, and there are voids in between. So this is, of course, something that we learned is because, of course, of gravity and all of the matter getting closer and closer together because of gravity. And on larger scales, all of the galaxies are grouped together in galaxy clusters. And these galaxy clusters are then grouped together into these filaments. This is definitely one of the reasons that this is made possible. Our at least understanding of that is because we have telescopes in orbit and on Earth, both of these in different wavelengths. So, for example, you've mentioned in my thesis that I mentioned some gamma rays. So I during that time I used some data from gamma ray telescopes, and here on Earth we have telescopes that show us visible light. But all of these information are just like tiny puzzles that we combine together to really learn about these objects.
So what does that process look like? You're trying to assemble the puzzle piece from all these different parts of the data set. Walk me through what your basic workflow is like.
So there are a lot of people involved in this, definitely. So I consider myself more or less the end user. So we have, different collaborations. So, for example, there is a collaboration around the Fermi Gamma Ray Space Telescope. So that's the one that I've been using in my thesis. And all these people observe the sky with this telescope, and for a very long time, for a couple of years, they have to reduce this data and understand it, and package it very well, clean it. And then the other scientists who are the end users can really use the clean data set without all of the other things that maybe we don't care about in these observations. And then you have many collaborations, many different telescopes doing the same thing, observing the night sky for years and getting better and better precise data that they will clean and make nice and presentable for every other user to use. Until now, I've been mostly involved in just using the data, not cleaning it. But now, since I moved here, for example, at Fermilab, where I work now, here in the suburbs of Chicago, I'm witnessing more and more the whole process of how the whole workflow looks like, how the observations are done, how the data reduction is done, how to store it, how to move it. All these are very big data problems. And Fermilab is luckily a premier national lab involved in many big collaborations. So now I have a more like a front row experience of how these things are done.
And then, where do you come in that process? Because one thing I've mused before is that at a certain level of abstraction, all data problems end up kind of looking the same. Like it's probably a CSV, sitting on S3 somewhere, and you're pulling it down into pandas. So when you work with this data, it's clean presumably, and what are the tools you use for that?
So me personally, when I use the data, usually until now, I've been using clean data, at least when it's observed. What I do, I like working mostly with images because I like deep learning, right. And that's what I currently do. So it's not that hard to get the data. The databases are very well organized. You have a lot of astronomers you can talk to and computer scientists who kind of help you through the whole process. You have to know what you're looking for, definitely, right. What type of objects. Because in astronomical data, you have a lot of data, but really you don't have like if you want to do some kind of machine learning, for example, with them, you don't have, clear labels. You have to make them very often, because especially if it's new data, it's not the same like working with, cats and dogs.
Right.
So there is a lot of we have to figure out how to do these things, how to figure out which objects we want. Are we, correct about how we classify the object that we're observing, and how to get the data that we need for a particular physics study. But other than that, it's not that hard. The bigger problem have people who have to clean the data. So sometimes the telescope doesn't work. You have a very bad day.
Right.
Sometimes, part of the telescope, like one part of the camera doesn't work, or a couple of pixels. And for some studies, that is a huge problem. So there are people who have to, go through the data, understand which things that can be used, which cannot be used. And that is, for example, one of the problems that I hope that one day we can automate with machine learning, because we have huge data sets now, but in a couple of years, we'll have vastly larger data sets that we have to go through. And there's a lot of, those pre-processing steps that we have to go through until the science can be done.
Yeah.
So that's one of the things that I hope machine learning will help us with, for example.
Well, there's also the generation of the tags. So that's probably enormously manual at this point as well, right?
Yes. Unfortunately, yes, especially when you have, for example, some objects that you couldn't observe before. You build a new telescope that has better resolution. And for the first time, you see, for example, some very faint objects like low surface brightness galaxies, for example. These galaxies have brightnesses lower than the night sky. So we couldn't observe them before.
Right.
So now somebody has to go through all of the data and find candidates for these objects and actually look at all of the images, classify them as potential candidate for a low surface brightness galaxy, for example. So that is very tedious, very slow. But for example, me and a couple of my coworkers have been working on doing this more, automated with deep learning, and it's showing a lot of promise. So I'm hoping that a lot of other tasks like these can be, vastly improved and faster very soon, because we'll need them to be faster.
Oh, yes, of course. Well, so let's just talk about that then. So I guess you came to my attention because you said at the intersection of astrophysics and deep learning. So what are the deep learning approaches that you're using to process these data, and what are the advancements you hope to make in the future?
Mm-hmm. So my current interests have a couple of different fronts. I guess to continue from what I've previously mentioned, the low surface brightness galaxies, and objects similar to these. We, for example, use mask RCNNs, so object detection algorithms. So the same things that self-driving cars use to detect trees, pedestrians, etc. We are using the same things to train the network to recognize the objects that we care about from some, for example, similar looking but still a nuisance type of objects, and find them. And that is also, I think, going to be very useful for finding weird phenomena, maybe, or transient phenomena where you have something, weird happening, and you really need to, for example, react very quickly. That does happen in astronomy, even though most of the things last millions of years. Some things don't. Some things last, a couple of minutes, a couple of weeks. And sometimes you really need to react really quickly to send alerts to other observatories, and so that you can observe this object, for example, on a different wavelength. And those are the things that I think machine learning at some point will prove very useful as a tool.
What are transient phenomena in astrophysics? I'm having a hard time imagining anything that lasts 2 weeks in astrophysics.
Oh, but it does. So yes, so one of the very important transient phenomena are explosions of stars, for example, so supernovae. So when the star is like at the end of its like fusion cycle, fusing, hydrogen into helium, and all the way to iron. Everything after that, nothing after that really can be created through this process. And stars explode after that, creating all of the other elements that you have in the periodic table. And so these explosions are, of course, very, quick processes. And the way the light changes during the explosion also changes really quickly. So to really understand, we already know quite a lot about these processes, but still it's very crucial when we want to observe them that we catch the whole process. So as soon as it explodes, you observe it for, a couple of weeks to see how the light changes and decreases, just to see how strong it was, what type of explosion it was, and, you can learn a lot of other things about the object also.
So did I hear you to say that the heaviest element that can be formed in nuclear fusion in a star is iron?
Yes.
Why is that? Just that's the way it works out?
That's the way it works out. So the temperature and all of the pressure inside the star is contrasted also with gravity, and it just turns out that the all of the things that you have inside a star can really just make everything up to that element, and for everything above that you need more energy, and so that happens only when the star explodes, and it seems very strange and bizarre, but all of this, the universe is very vast, and there are so many stars, and so many stars exploded until now. So that's why even on Earth you have a lot of uranium and other heavy elements, and it's very interesting to just try to understand the fact that all of these things just came from these explosions of stars, nothing else.
Yeah,
that's the only way
remarkable.
to produce.
So when they explode, I don't know. Maybe I just have a very naive model of star explosion. It's not something I've spent a lot of time thinking about. But how is it that you get all the other elements in the periodic table of the elements? It seems like the energy would be fairly uniform throughout the explosion, and you would tend to get a relatively small constellation of elements. Or is that not true?
It's just a very huge burst of energy. And in this process, this is a very rapid process, but also I'm not a nuclear physicist, so I never worked on like exact models of how this is done. But because you have so much energy, and because not all of these elements are stable, sometimes you can create a very large element that also decays into everything that's smaller than that. So basically, it's just a combination of all of these things and producing all of kinds of elements and them decaying or fusing into other elements, and just in the end you end up with everything that we know.
That's amazing.
Yes.
So with these technologies, you said they're CNNs, right? So the convolutional neural networks is predominantly what you're using. What are some of the major challenges in deploying that technology? Is it mostly a matter of training? Is it just the case that astrophysicists generally don't really know how to work with them? What would it take to kind of scale that up a lot?
So there are a couple of challenges. So one definitely good thing would be if just we had more manpower, and especially more computer scientists who just devoted all of their studies to deep learning and advancing these methods. Even now, even with what we have, the number of papers that are published every day in astrophysics and in physics in general, using some kind of machine learning method, is generally like exponentially growing. So we are using it more and more, definitely. Having more people getting involved, also people who just study computer science, will definitely help. But even, if we put that aside, of course, more money and more manpower is always a good thing. There are challenges in how you apply methods in science. So first challenge is that the data is never very nice and clean, and it doesn't look like, as I said, cats and dogs and cars and trees. It just, in astronomy, it's often very noisy, the signal is very faint, so things look just different.
Is that just because the granularity of the image isn't very good because it's so far away?
Yeah.
Okay.
I mean, some images are, of course, really good, but overall the objects are, they don't have nice, precise edges.
Right.
They're not clear. There are, if you're studying a galaxy, there's a bunch of other things in the same image, other stars, other galaxies overlapping. And the better the telescope that we have, the more objects we'll see. So more objects will be overlapping with other objects in our images. So it's going to get harder and harder to distinguish individual things in images. So that's one of the things that people are currently working on, how to work on this problem. The other problem, which isn't a very big problem in my opinion, and something that I care about and I study currently, and that is how to bridge between different data sets. So in astronomy, deep learning, no deep learning, it's always useful to combine multiple data sets, whether that is from two different telescopes or that is from a simulation, which we use a lot. So we simulate some physical processes and observations. If we can use deep learning with both data sets at the same time, we will, learn from the differences, from similarities, and that is not easy to do. And so sometimes we need to, for example, simulate something, and we simulate a bunch of galaxies doing something. And when we have a simulation, it's super easy because you know what you're simulating, you have the labels. So it's very useful to start from the data set that you know, where you are. If you're working with images, you have all of the things that you care about labeled. And we can train on that, but we want to, of course, apply it to the real galaxies, and they're never going to be exactly the same like the simulated ones. And of course, the performance of the model will drop. So we need to basically develop methods that are going to allow us to kind of start from the simulations, but really have something that works on real data, especially if we want to use models in real time to help us find something, for example, in the new data. So these methods are, for example, called domain adaptation. And I've seen them being used a lot for, self-driving cars. You want to be able to drive a car in LA, but also in Chicago that looks differently. And so these type of problems I want to kind of apply to astronomy also.
Well, could you talk to me a little bit about domain adaptation? Because I'm a machine learning engineer, but I've never really worked on those kinds of problems before. So I actually don't know much about it. So what does it look like when you train a model that also generalizes well to other environments it's never seen before?
Mm-hmm. So the methods that I try to use, they basically allow you to have one data set that is labeled and a similar data set that is not labeled, but is the only thing that the model will know, for example, is that it's from a different data set, the different data domain. And domain adaptation really allows you to build the model during training so that it only uses domain invariant features. So only the features that it can find from both data sets at the same time. And sometimes, of course, these are not maybe going to be the most useful and most obvious and easy features for one of the domains, but you don't care about that. You just want the neural network to find something that is common in both data sets. Because without that, even the simplest examples that I've tried without domain adaptation just don't work. So I train on, for example, I create galaxies. And I train on them. I create simulated galaxies, and then I just and then I just add the noise. So it's the same data set, just add a little bit of noise, and the model doesn't work at all. So this is definitely going to be, it's crucial even now, but for in the future, I think that if we want to use domain adaptation, in any kind of application in astrophysics, I think we'll need to do something like that.
Yeah, so it strikes me that that's sort of a broader variant on the concept of regularization. So you're preventing the model from overfitting by forcing it to find more robust abstractions that will generalize across data sets that otherwise don't bear that much resemblance to each other. Is that right?
Yes, exactly. And especially if you have a big model, which I don't like using all the time, but for example, if you use one of the standard ones, so use your ResNet, for example, what I've noticed is that when I use domain adaptation, not only it allows me to work in both data sets, but it also helps me increase the accuracy even on the easy data set that I have where I have labels for, because it's very easily starts overfitting. So I have to stop the training.
Right.
With domain adaptation, that doesn't happen. So it's helpful actually for both data sets, for the new one where you don't know the labels, but also for the old one where you have the labels.
I got you. And when we're talking about data sets, I'm sort of imagining images. That's what we've been talking about so far. But what are some other data points that you use?
I've been mostly talking about images because that's what I mostly use. But a lot of astronomers don't use images. They have either data, they're just numbers that show you some specific physical parameters about the objects, and they in that case use not deep learning that works with images, not CNNs, but just regular machine learning algorithms that work with numbers. And sometimes you also, for example, don't have an image, but you have maybe a spectrum. So it's like a 2D data where you just have a spectrum that can be work with as an image or as a set of numbers. And people do both things. They sometimes find interesting features in this spectra, even if they just look at them as images, work with them as CNNs. This is also interesting.
Oh, that's fascinating. So what are some of the mysteries that you're working on now, like the astrophysical problems that you're trying to solve?
So one thing that I'm really interested are galaxy mergers. So I use mostly deep learning to try to kind of understand it better. But the reason why I'm interested in galaxy mergers is that these are extremely slow processes. So galaxies very often actually merge, but just this lasts for millions of years. So for example, even Andromeda Galaxy that is very close to Milky Way, it is going towards us and eventually will merge, or at least go very near Andromeda Galaxy. And galaxy mergers are kind of a crucial thing to understand if you want to understand the evolution of matter in the universe, because we have different types of galaxies. Perhaps you've heard about spiral galaxies or elliptical galaxies, irregulars. And we believe that one of the reasons why we have different types of galaxies is because of mergers. So depending on how the two galaxies will merge and what are their masses and how they approach each other, one of the reasons why galaxy mergers are very important for astrophysicists is that even though these are processes that last for millions of years, we now believe that depending on which type of galaxies are going to collide and how they approach each other, basically you can get as the end result from this process different types of galaxies. So you've probably heard that we have spiral galaxies, we have ellipticals and irregulars. And probably the reason why we have that is because of galaxy mergers. The tricky part is that these are very long processes, as I said. So you cannot observe a pair of galaxies colliding. So you have to have really build big data sets of galaxy mergers in different stages. And that is not easy. It's not easy even to recognize if something is really a merger in observations, for example. So sometimes you will have galaxies that look like they're very close to each other, but they're nowhere near each other. They're just looking like they're very close because we just have, and so really finding a lot of examples that are trustworthy, understanding, which objects are really merging, and combining that with simulations of galaxy mergers and the properties that we can learn from this simulation. We can see the end results. We can, compare them to what we observe, and really learn about this process. And I'm fascinated about that. I have always been very interested in the formation of structures that we see in the universe at different scales. Ever since I started working as an astrophysicist, I cared about this. And so, now I study galaxy mergers as, again, a process that is very important for structure formation.
When you put these models together and you go out and you find galactic mergers, are you just trying to find two galaxies that are currently in the process of merging? Because you said it's kind of hard to tell, right? So presumably there's got to be a finite number of galactic mergers that are currently ongoing. So what's the ratio of gathering the empirical evidence versus building these rather speculative models that allow you to get purchase on this problem?
So there are a lot of mergers in our data. The problem is that you have to gather more evidence for each merger to be sure that they are a merger. So if you just have a telescope that observes, in optical light, you will not be sure if that's the case or not. One of the reasons is just because you only have the light and you don't know how they're really moving. To know how galaxies really, behave and how they're moving, you need to get their spectrum, for example. So in the spectra of galaxies, you really have, so the spectrum of a galaxy shows you how the light at different energies or different wavelengths is distributed. And in these spectra, you have some emission lines and some absorption lines from elements. And these lines really tell us what kind of composition, like chemical composition it is in the galaxies. And we know exactly how each element really behaves. We can experimentally measure that on Earth. So we look for the same signatures in galaxy spectra. And when galaxies move, so it's the same like when the car moves towards you. It will change the pitch of the sound that it's making. And the same, we're looking at the same signatures in the spectra of galaxies. So you look at how these emission and absorption lines move, basically. And this movement will tell you, is the galaxy moving towards you or from you, and how fast? And basically, by looking at pairs of galaxies and looking how they move from the spectra, you can actually get the velocities and which directions they have. And then, and only then, you can know that they really are interacting. So that is slow and hard to do. You have to have a good candidate, then have time on the telescope that has a spectrograph, then observe that. So that's very tough. So we're hoping that maybe with machine learning we can extract more information from images by having a very trustworthy data set that maybe has more information from different sides, learn something, how to really understand what the merger is, what's a fake merger, what's a real merger, and then maybe just find new candidates. That would be very helpful for future studies.
Okay. And then what is it that draws you to this problem? Like what are the questions you're hoping to answer? Because it sounds like just a really, really cool thing to study, but naively, I'm just sort of imagining, well, the galaxies kind of merge and some stars crash into each other and there's a bunch of elements formed and ejected, but it's not obvious to me what the great scientific mystery is there.
Well, I believe that the big mystery that we're trying to solve is the mystery of how galaxies, came to be. How is it that the Milky Way came to be the way it is now, and that in the end, we could be, created here and living here? So how do we get to the, physical state that our galaxy has? So that is one of the things that definitely is, part of the process of understanding galaxy formation and galaxy evolution. Finally, understanding how stars form. Because, for example, star formation is not the same in all of the galaxies. And as we mentioned already, stars are crucial for producing elements, very heavy elements.
Right.
So the number of stars that is born in each galaxy is not the same. And for example, we see that some galaxies have a lot of new star formation, a lot of young stars, and some don't. And we actually believe, again, that galaxy mergers are to blame. So depending on whether the galaxy had a merger and how far in the past, it will either have a lot of stars or it will not have a lot of stars. And so, again, galaxy mergers really are the creators also of stars. And stars are, finally the creators of the elements that we have around us. And, the possibility of creating life in the end.
So is it just a matter of a galaxy that is very old and has experienced no mergers recently eventually just runs out of its stars? Eventually they just run out of their fusion cycle, they explode, and that's kind of the end of it. And if there's no other inputs, if they don't merge with anything else, then there's no engine by which more stars could form. Is that basically right?
Yes, but I can't say that we really have a complete consensus of like whether mergers help create or destroy star formation rate in galaxies. So sometimes perhaps a merger can be the reason why the galaxy stops forming stars. But then again, that's because we don't fully understand the whole process. And while studying galaxy mergers will hopefully eventually, make us certain of how it actually influences the whole thing. But yeah, most of the time you will have a very old galaxy, as you said, that either didn't have a merger or had it very long time ago, and then it has a lot of stars that are just slowly quenching and dying.
Why would a galaxy merger stop star formation?
I would like to have a good answer to that. But I don't know.
What makes anybody think that it does, right? Because I mean, like I said, and this is just me responding as you're talking. I'm just thinking like, well, there's things crashing into each other. That's new matter. Maybe it could accrete around a common gravitational sink, something like that. But I have no idea how it is that a merger of two galaxies would stop star formation.
The merger can really it moves the gas around. It moves all of the matter inside around, and so also we have to take into the consideration that maybe some galaxies, probably have dark matter around them, that we also hope to understand better through these processes again, the way all of these different particles and different types of matter interact will eventually either help things clump and heat up and increase the star formation rate, or maybe it won't. I think that just to be completely sure, we have to have just more data and more studies and more also like people who are doing simulations to really, better understand the whole process. I don't have a better answer. That's why this is a thing that we like to study to understand.
Yeah, well, there's so much for you to do, right? Because we're not really sure what this means or how it works. So, to what extent does your work interface with dark matter? So this is something I don't understand very well. I hear it kind of spoken about a lot, and I've just always kind of wanted to pick the brain of an actual scientist who studies the skies. So could you shed some light on dark matter for me?
So my work is, mostly related to the visible matter. But as I said, each galaxy has, at least we assume, has a lot of dark matter around it. So around every galaxy, you have like a halo of dark matter. We still don't know what that is. And there are a lot of people at Fermilab, both theorists and experimentalists, trying to figure out what dark matter could be. Is it a special type of particle that's maybe interacting in some way with the regular matter and with many other ways, it doesn't interact. And the reason why we believe, and we, have these observations for a very long time now, why we believe that there's dark matter around galaxies is that if you observe a spiral galaxy, moving around, and you measure the velocities of different data of different points in the galaxy, some of the velocities as you go further away from the center are just too large. So if there is nothing holding, no additional matter holding gravitationally all of this matter, the galaxy that it's rotating with that speed would just, disintegrate like things here on Earth when you spin them. So when, people observed this for the first time, they measured these velocities, they saw that they're just weirdly high, that there must be something else that we don't see that's holding it. And we still don't know what it is. People have been, trying to figure this out for a very long time. But yeah, a lot of observations from, different telescopes might help us do that, to just observe the things that we can, see how they, move, how they interact, to better understand the things that we don't see. And also some people who are just theoretically trying to figure out what kind of particle is that, what can be a particle that doesn't interact with the regular matter.
So it's a question of the velocities being much too high, and our belief that if there were nothing else acting on these galaxies, then the stars would fly away, right? So if I've got beads on a string and I start spinning it at a certain velocity, they all come off. And if they don't, you assume there's something else operative, right?
Yes.
So why couldn't it be something like a black hole, or like why stipulate this, non-baryonic particle that doesn't interact with things in weird ways and isn't photonic, and it seems like an awful lot to add to it. And I mean, the people working on this are far smarter than me, so I'm sure if there were a simpler explanation, they would have come up with it by now. But it seems a lot like epicycles.
So, especially theoretical particle physicists are also, I think, a lot smarter than me. So definitely the detailed answer would be something that they would give you. One thing that I can say is that, at least on this example of velocities of galaxies, you need a lot more mass to hold all of this thing, all of the matter that you do see just inside a galaxy. And just having a black hole isn't enough. So this is not something that could be, helpful enough, even though we know that in the center of most galaxies, you just have a supermassive black hole. But that's not enough. One reason why I think people believe that it might be some kind of new particle is that everything that we do see and have in our experiments on Earth and we observe, most of the things that we understand really fit very well in like the whole standard model of particles that we know and how they interact and all of the forces that they interact with. But somehow some observations like these don't fit the picture. You just have to have something additional. Yeah, even on large scales, people who create simulations of how the cosmos evolves, like so from the Big Bang to today, to like having these filaments that I talked about, large scale structures. If they imagine different type of dark matter particles and different types of potential forces they can interact with, they end up with a different looking universe.
I see. So
they can really test their hypothesis in a simulation to see if their hypothesis for a particular type of dark matter really works. Do we observe the universe that looks like that, or it doesn't?
So that might be part of the answer to the next question I have, is that why do we stipulate that dark matter forms halos around galaxies? Why wouldn't it suffuse the galaxy or just be evenly distributed throughout the universe? Is it just because, well, if you do that, then you don't get, it has no explanatory power at that point?
I guess people imagined that there must be something else that maybe also, gravitationally is bound. And if it interacts gravitationally with the regular matter, that would, help it to hold together during rotation. So if it does interact gravitationally, it should interact with itself too. So it would form like a cloud, for example, around the galaxy, like a bubble that the visible matter is just located inside. So yeah, I think that just because we hope that we understand at least substantial amount of physics, we don't want to invent too many new things. And I think that the things that we do know kind of maybe logically lead to a halo of dark matter.
I see. Well, that's very interesting. No, this is all stuff I'd never really heard of or thought much about. So I guess in the 10 minutes we have left, would you mind telling me a little bit about the Deep Skies project that you're a part of?
Yes. So Deep Skies Lab is an awesome community that I've joined a couple of years back. It's a community that, gathers astrophysicists who really care about implementing and developing machine learning and deep learning methods for use in astrophysics and in sciences. It is a community that has a lot of astrophysicists from around the world, not only from US, but also has people who are, non-astro, maybe regular physicists or even computer scientists who are interested, in helping us out or, generally are interested in astrophysics. People who are scientists but move to industry and now maybe know a little bit more about, different applications and they have different ideas. Scientists who are not physicists, have, people from geology or medicine, biology, and all of these people are really using machine learning a lot. So it's a really cool community where I learned a lot from all of them. You can learn a lot quickly. You can join different projects, help out. We have, journal clubs, educational clubs, and, all kinds of things that can really help us all do science faster. We have students, we have even some high school students, not only like undergraduates and graduates. So this is a really cool, welcoming community that really is focused on advancing deep learning and machine learning for sciences.
Are any of the data sets open source? Is that the sort of thing I could pull and run some analyses on?
Yes. Good thing that, the Astro community generally, a good thing about Astro community is that many data sets are very public. So many clean data sets are public, and compared to maybe some other physics experiments where things are either not always public or they get public later on, astronomy community was always very open to publicly, allowing people to access the data sets. Not everything, but a lot. It's probably because we have so much of it.
Right.
so that there's definitely not enough people who can, handle all of the data, and we're just going to have more. So yes, if people are outside of Astro and are interested in helping out, there's definitely always, things to do, data sets to access. And finally, if somebody wants to join Deep Skies and he's not a scientist, it's, free to apply and join and, talk to us. We can, help you get access to different things.
Well, that's a remarkable effort. I asked a version of this question earlier, but I kind of want to step back a little bit and just inquire as to, are there like one or two questions that you would like to see answered in your lifetime that if you worked on and there was a solution or a breakthrough, you would die happy someday? Or is there anything like that for you?
Well, there are a couple. I would really like to have, better sense of what dark matter is. I would like to have experiments show us what type of, hopefully a particle or maybe something else it is. I would really like to also understand dark energy, where it's just as weird
Yeah.
as dark matter. And, we currently think that the dark energy is like 70% of the whole thing in the universe, whole energy and matter. So, I don't know if those are the questions that will be answered, in the next few decades while I live, but I would certainly be happy if at least part of it is answered.
Well, I think that's a wonderful answer and a wonderful set of goals. And thank you so much for talking this over with me today.
Thank you so much for inviting me. This was really a pleasure. Thank you.